What is the associated oxyanion? Who and their neighbor have an answer? If you need another one, I got plenty. Okay. Kenzie? For acetic acid. What's the name of that ion? Acetate. It's the acetate ion, and the acid is called acetic. So the names have a connection. But if we look, this part, CH3COO1-, that's the acetate ion. So most of those oxyacids are related to a polyatomic ion. Okay? If you look furthermore at the bottom of your reference sheet, you'll notice that I've given you a box with formulas for some common acids. These are the ones that we use the most. Again, I don't make you memorize them because you're going to look them up and you're going to get them memorized. By the end of chapter 9, certainly, you're going to just know the formula for hydrochloric acid, for sulfuric acid. You won't even have to look it up, but you'll do that by looking them up. Okay, salt. Salt is not what you think it is. Yeah, that's a good question. Just to go back to acids for a second. They pretty much all contain hydrogen. And when we get into acid-base theories in chapter 15, you'll start to see why, because there's a whole thing with donating hydrogen and accepting hydrogen in acid-base reactions. Okay, salt is not what you think it is. What do you think salt is? Go ahead. Somebody give me the answer. The obvious answer, you're all thinking it. Or tell a friend. You're too chicken to tell me. It's a lie. Well, it's not. We have the everyday common speech definition for salt, which is what? Sodium chloride, table salt. In chemistry, a salt is an ionic compound, and it's a cation, and it's the anion that specifically comes from an acid. So NaCl is one example of this. So if we take sodium hydroxide, this is household lye. It's a drain cleaner. We'll use it when we make soap. We do a soap making lab in chapter 9, and you'll use sodium hydroxide. It's a base. It's an alkaline substance. It's nasty, nasty stuff. If we mix that with hydrochloric acid, we get two products. So the sodium and the chlorine form NaCl. And then the hydroxide ion and the hydrogen ion form something also. What do they form? What is that? Yes. So basically, you put an acid and a base together, they neutralize, you get a salt, and you get water. And we'll run some neutralization. You've actually all probably run a neutralization reaction in your lifetime. Who here has mixed acetic acid with sodium bicarbonate? What'd you do?
Doesn't it, the baking soda and it reacts like
Yeah, baking soda and vinegar, acetic acid and sodium bicarbonate. And you get out of that sodium acetate as a salt. Okay, so, there's hydrogen bicarbonate. You can take, here, we'll do that one. So you can take sodium bicarbonate, HCO3, plus HCH3COO. And this one's a little bit more complicated because you get some, you get some CO2 out of it. If you've done baking soda and vinegar, you know you get CO2 out of it, right? It bubbles. you also get the sodium acetate. I'm going to run out of room here. Gesundheit. And you still get some water. So you get three products. Gesundheit. So salts are not just what you think they are. So is potassium chloride a salt? Yeah. You've got an anion, which could come very easily from an acid, from something like HCl. You've got a cation, potassium. Magnesium bromide. Is that a salt? Yeah. Salts are basically ionic substances where you've got a metallic cation and an anion that it can come from an acid. So most of your ionic compounds, you'll hear things referred to as metal salts. If you ever get a chance to look at things about firework construction, the things that make fireworks all the pretty colors, and you know this from the flame test lab, you know that a lot of metals such as sodium, potassium, lithium burn with distinct colors. The form that those go in to the fireworks, get packed in with the gunpowder, is in the form of metal salts. So you'll have potassium chloride or lithium nitrate, and those salts are what you see the colors in the fireworks coming from. Okay, now the big thing for the day. Oxidation numbers. What does oxidation mean? I'm going to be completely honest with you in the interest of full disclosure. I had a year of high school chemistry. I had a minor in chemistry in college, which means 2 years of chemistry. And I've been teaching chemistry now for 8 years? 7 or 8 years. I don't remember. It all blurs. It's probably really only a couple years ago that I think I fully understood what oxidation meant. Nobody ever explained it to me in high school chemistry. In college chemistry, they don't really explain anything to you. You have to fight with the material yourself. You get your 4 hours of lecture a week, and it's you and the book and the homework and office hours. You can go in and ask for help, which I don't know what to do when I was in college. Oxidation, and you've probably heard about, we talk about free radicals and oxidation in cells. Have you heard that? Anybody heard the term oxidation anywhere? Oxidation, where have you heard it? Oxidation of metals, so formation of rust on a metal. We talk about the iron oxidizing. So this was great, and another teacher gave this to me. Leo says, grrr. Lose an electron, oxidation. Gain is reduction. We're not going to talk about oxidation reduction reactions, but the only thing that you need to remember here is Leo. Lose an electron, oxidation. So oxidation is all about how many electrons you've lost. It's about your relative, when we say oxidation number, we're talking about your relative charge. Relative charge. When we say something is relative, what are we saying? So, am I tall? I'm actually average for an American female. If you put me in a room full of kindergartners, am I tall? I'm relatively tall. If you put me on a bus with a bunch of people from the WNBA, am I tall? I'm a midget. I'm teeny tiny. That's relative height. We're talking about how tall I seem in comparison to the people around me. When we're talking about relative charge, we're talking about how this element has gained or lost electrons relative to the things around it. So this is a way to indicate general distribution of electrons. It's only in bonded atoms. And it's only in molecular compounds or polyatomic ions because no electrons have really traded place here. Okay? No electrons have actually traded place. Nobody's actually given up an electron. Nobody's actually gained one. Where in an ionic compound, we're talking about something that actually completely lost an electron or completely gained a new one. Here, this really comes down to more like electronegativity. You know, who's holding those electrons more tightly? So, for years and years and years, I thought these were really dumb because they are made up, in a sense. They're relative, but they have their uses. When you do Lewis structures and there's more than one possibility for a Lewis structure, which happens sometimes, using oxidation numbers versus formal charge is a way that, you know, far better chemists than I will say, oh, this is the correct structure, not that one. So we're going to practice doing oxidation numbers. If you look at the bottom of your reference sheet again, I've packed as much stuff onto here as I possibly can. There's a little tiny box that has very abbreviated rules for assigning oxidation numbers. When you take the test for this chapter, you will have this reference sheet because the rules for assigning oxidation numbers look like this. And I think that's crazy. I would not expect you to memorize those for a test. That's a waste of your brain cells. So I've given you an abbreviated version of the rules. The question is, can you use those rules to assign oxidation numbers? So the first thing you got to know, if it's not bonded to something else, if it's a pure element or it's just bonded to itself, the oxidation number is 0. So, quick, what's the oxidation number of that? 0. Oxidation number is 0. What's the oxidation number of that? 0. It's a pure element. It's bonded only to itself, so the oxidation number is 0. What's the oxidation number for sodium? 0. These are intentionally easy. So if it's a pure element, if it's bonded only to itself, or it's, you know, so here, S8, sulfur's a weirdo. It occurs in these clusters of 8 sulfur atoms. Oxidation number on sulfur here? 0. We're actually assigning every single atom in a compound its own oxidation number. When we look at something like, sulfur hexafluoride, you drew this big ugly thing. You built it. You measured its angles. Which one of these is more electronegative? Hands down, fluoride, fluorine, fluoride ion. Now this is not ionic, but because this is more electronegative, we say that the oxidation number on the fluorine is what it would have if it formed an anion. What anion does fluorine always form? Fluoride, which has got what charge? 1 minus. So, you know, the oxidation number on fluoride equals 1 minus. The less electronegative element has the number that it would have as a positive charge, but we work off the negative oxidation number. Fluorine is always -1. Oxygen is basically always -2. There are a couple exceptions, but in essence, we're never going to deal with them. Okay. Hydrogen is generally +1. And there are some exceptions again, but we're really not going to deal with them. It all has to balance out, just like in ionic compounds. So the sum of the oxidation numbers has to be 0 as long as the compound's neutral. If it's polyatomic, sum has to equal the charge of the ion. We're going to just go ahead and start practicing now, because I think it makes more sense when you see it done. This is one of those things where it's kind of a process. We walk through it on every single one, and you have to go back, flip back to the rules and look for which rule to use. So, cut. So this is uranium hexafluoride, and we could use sulfur hexafluoride to the same effect. I typically start these off like this, and what I'll do is I'll write the oxidation numbers over top of the compound. So, do we have a rule for either of those? If we go back to our rules, whoops. Yes. Based on rule number 3, what's the oxidation number on fluorine? -1. So, we have 6 fluorine atoms here. What's the total negative oxidation sum for fluorine? So -1 times 6. -6. So whatever number is here has to algebraically mesh with that so that it's equal. So this plus -6 must equal 0. This is an easy one. What's the positive oxidation state on the uranium? +6, yeah. Now, how many uranium atoms do you have to divide this up over? Just 1. So I tend to do this, divided by just 1, which means that the oxidation number on each uranium is +6. There's only 1 uranium. So basically, I start from whatever, and usually we start with the most electronegative, what would be the negative cation, and I kind of work my way down, over and back up. I find that to be kind of a useful way to do it. Let's do one that's a little tougher. Let's do one that has 3 things in it. So we'll do H2SO4. Do you remember what compound that is? We just talked about it earlier. It's related to it's sulfuric acid. Nasty, nasty, nasty stuff. So, sulfuric acid. Do we have a rule for any of the compounds here? So flip back to your rules. We have a rule for oxygen. We have a rule for hydrogen. So let's start with our most electronegative. And we're going to make sort of 3 columns here. I should spread these out a little bit. What's our rule for oxygen? Oxygen has an oxidation number of what? -2. And we have how many oxygens? 4. So times 4, we have here -8. We also have a rule for hydrogen. What's the rule for hydrogen? +1, yeah. And there are 2 hydrogen. So here we have +2. Now, this is our big blank. So what we know is that whatever number goes there has to make the algebraic sum equal 0. So we, in essence, have positive 2 plus x plus negative 8 has to equal 0. What's that number on sulfur? Gesundheit. 6. So we have to have a plus 6 here. How many sulfurs do we have to divide that up amongst? 1. Divided by 1, we have a oxidation number on sulfur of plus 6. That looks like an H. It's not. Now, a couple things to note. This is not the oxidation number. That's part of your calculations. The oxidation number is on each individual atom. So here the oxidation number on hydrogen is plus 1, on sulfur it's plus 6, and on oxygen it's minus 2. What that means is the oxidation numbers on each atom don't total 0. It's only once you've multiplied them out by the number of atoms that you've got of each thing that they're going to have an algebraic sum of 0. Okay? In your homework, you've got oxidation number problems, so I'm going to have you get started on those, and that's it.